About pH. Now, pH is something that I'm sure a lot of people have heard of, but very few people really understand what it means. All right. Now, the pH scale is what we're going to start off with, and some of you guys might even know that pH is like a number scale that determines the acidity of a substance. All right. Now, the scale basically it's a numerical scale used to express acidity. Now, any pH less than 7, the solution is considered to be acidic. If it's greater than 7, then technically it is basic or alkaline. And then if it's equal to exactly 7, like pure water, then it is considered to be neutral. Now, here you have an idea, just to give you, just a fair idea of what are some of the pHs and some things that you may have heard of. Pure water is 7. Blood is actually slightly basic. All right, it's a little bit basic, whereas milk is just slightly acidic. And then as you go further and further down the scale, you get more to like vinegar, then lemon juice, stomach acid, so forth and so on. And then above it, you have bases such as ammonia and all the way up to sodium hydroxide. Now, what pH it is itself, though, I mean, this is just basic stuff here. pH itself is a bit more complicated. You see, what it is the negative logarithm of the hydronium ion concentration in solution. And the basic formula is here. pH is equal to the negative log of the hydronium ion concentration. So if you're trying to figure out, well, what is the concentration, the pH, all you do is you just follow the basic steps. You push the plus minus button to give you the negative. Then you push the log key, which is one of the keys on your calculator. And then you enter in the hydronium ion concentration. Very, very simple. I will be showing you guys an example of that later. But it can basically be very useful. Now, if a Ka, one can also use Ka to determine the hydronium ion concentration for weak acids. I have a sample problem video where I showed just that in the previous lecture on the strengths of acids and bases. And if you have the Kw and you have, let's say, the hydroxide ion concentration, well, you can use that to find the hydronium ion concentration for bases. All right. So there's a way of working around it, as it were. Now we have from there. One thing I do want to point out is that the relationship of hydronium ion concentration to that of its pH. If you notice that as the pH decreases, right, you go from, let's say, a pH of 3 to pH of 2, every time you go down 1 pH, since it's a logarithm base 10, what that means is that you are 10 times more hydronium ion concentration. If it goes by 2 pH, let's say from 4 to 2, then you are from times 10 negative 4 to times 10 negative 2. It's 100 times more concentrated of hydronium. All right. So every time you go change pH by 1, it goes up or down by a power of 10 for the concentration of hydronium. Now, as far as significant figures, it's done a little bit differently. If whatever the number of significant figures there are in the concentration, that is how many decimal places past the decimal that you need to have your pH in. So if you notice here, it's 1.0 times 10 negative 5 molar. Therefore, the pH is 5.00. Two significant figures means that you have 2 places past the decimal. If there was one significant figure, then it'd be 1 place past the decimal, so forth and so on. Okay. Now, neutral solutions, of course, have a pH of 7. And since the concentration of hydroxide and hydronium are equal to each other, as I mentioned before, all right, basically, this is how you get the pH of 7. Since the Kw is equal to 1 times 10 to the negative 14, all right, 1 times 10 negative 14, then the hydronium ion concentration would be basically the square root of that, which is 1 times 10 negative 7, and the negative log of 1 times 10 negative 7 is equal to 7. And if you want to go backwards, if you have the pH and you want to figure out, well, what is the hydronium ion concentration, then you have to use the inverse log. Now, if you never realize this, the inverse log is your 10 to the x button. All right, on most calculators, it's the secondary function on your log button. So the basic formula is, again, you have to do that negative to take care of that. It is 10 to the negative pH. That's what the hydronium ion concentration is equal to. All right, and here are the basic steps for that. You go and push your 10 to the x button, then negative, and then your pH value. All right, and I have a couple of sample problems that I wish to show you, and here they are. Hi, here we have a couple of sample problems that involve pH and how to use your calculators for it, and also a bit how to navigate around using, the various tools that we have learned. Now, in this case, the question is, what is the pH of a solution of sodium hydroxide? Okay, and they give us a concentration of sodium hydroxide. Now, there is something that hopefully you have. It's a little tool that I call an acid-base map. Now, what this basically does is, depending on where you're starting, what information they give you, and what the information the question is asking, you can use this in order to kind of navigate about. For example, this question is asking, what is the pH? So in a way, we're trying to find the pH. And the information that they're giving in this case is the concentration of NaOH. That's our starting point, and we're trying to figure out what the pH is. Now, this is a strong base. It's an alkali metal with hydroxide, so it's a strong base. Now, I'm going to be starting on this island, and I'm going to be going to pH way over here. Now, that means I'm going to have 3 basic steps that I'm going to need to do this problem. The first one is the easiest, and that is, hey, look, this is a strong base, and therefore its concentration of hydroxide is going to be the same, especially since there's only one hydroxide here. Therefore, these two are going to be equal to each other. So I know first step is that the concentration of NaOH, which is equal to 0.25 molar, is going to be the concentration of OH negative. So there's my first step. I now have the concentration of OH negative. Now I want to go and get to hydronium. That way I can use the pH, the log to find pH. So to get from hydroxide to hydronium, I'm going to use the Kw equation right here and know that, well, hydronium is equal to Kw over the concentration of hydroxide, okay? So Kw is 1 times 10 negative 14. OH in this case is 0.25. Therefore, on my calculator, I go 1 EE negative 14 divided by 0.25 equals. And I have 4 times 10 to the negative 14. Now, for significant figures purposes, remember this is a constant, I don't worry about that. I have 2 here, so technically that needs to be 4.0. All right, 4.0. Let me erase that, make that nice and clear. 4.0 times 10 to the negative 4.0 times 10 to the negative 14. Sorry about the bell. And then this is concentration. Again, that's a concentration of hydroxide. And then the last step is, in order to find the pH going in this direction, I take the negative log of the hydroxide. So I have that, which is 4.0 times 10 negative 14, and I want to take the negative log of it. So the way I do it is this. All right. I go, if you see right here on the log button, all right, it has a 10 to the x as the inverse. So I go negative, all right, remember it's negative. So I go the negative button down here. So clear that. Negative, and then second, sorry, not second, I just go log. It's not 10 to the x, sorry. It's log, so negative log, and then the concentration of that answer. So I'm going to go second answer, which is 4 times 10 negative 14. I push equals. Now, since this question this has two significant figures, all right, the pH, again, is equal to the negative log of the concentration of H3O, which is the negative log of 4.0 times 10 negative 14, okay? And therefore, since that has two digits, I need to go two places past the decimal. So the pH is equal to 1.3, and since that's a 9 after the second 3, I round it off, 1.34. And there's my answer. Now remember, with pH, there are no units, all right? No units. So that's the first sample problem. The second sample problem is kind of going in reverse. Here, it's telling me what the pH is, and it's asking what is the hydroxide ion concentration. So I'm starting with pH, and I'm trying to go to OH negative. Now, looking on my map, I see that, well, if I'm starting here on pH and I'm going to OH, it's going to be a two-step process. The first is to use the pH in order to get to hydronium, and then use Kw to get to hydroxide. So, first step is I'm going to want the pH, excuse me, my mistake. I have the pH, it's going to be the concentration of hydronium is equal to 10 to the negative pH. So that's going to be 10 to the negative, all right, sorry, not molar, it's just 3.4. Saw that, I was going, what's wrong with that? So the pH is 3.4, so it's going to be 3.4. So on my calculator, I go second, 10 to the x, negative 3.4 equals. Now here, I have 3.98. Now, I have one place past the decimal on my pH, so that means I only have one significant figure on my answer here. So I round it off to one digit. It is simply 4 times 10 to the negative 4 concentration. Remember, that is equal to the hydronium ion. My last step, now that I have hydronium, I'm trying to get hydroxide. I use the Kw equation to find the hydroxide. And remember, since Kw is equal to hydronium times hydroxide, if I want to find hydroxide, I would divide both sides by hydronium. Okay? And therefore, those cancel out. Hydroxide is equal to Kw over the concentration of hydronium. And therefore, I have 1 times 10 negative 14 divided by 4 times 10 negative 4. And according to my calculator, I have 1 EE, negative 14 divided by 4 EE negative 4. And I get, as my concentration of hydroxide, 2.5. Well, I have to round that off. So that's going to be 3, right? Because that only has one digit there. 3 times 10 negative 11 molar. And there's my concentration of hydroxide. Now, after those problems, just a couple more things about pH is, first of all, how is it measured? Well, there are a couple of basic ways of measuring pH. The first is through the use of indicators. Now, an indicator, we've used them before. An indicator is simply a substance that changes color, exhibits specific colors in solutions of different pH. And there's many, many different types of chemicals that can be used as indicators. Okay. Um, some are very specific, so forth. Some are combinations of these different chemicals. Now, the benefits of indicators is that they're inexpensive, i.e. cheap. They're quick to use and very easy to use, but they tend not to be 100% accurate. Or if you want to get very accurate with them, you tend to need to do very specific chemical processes in order to become accurate with them. For example, thymol blue is a type of indicator that whenever the pH is less than approximately 8, about 8, then it turns yellow. If it's greater than 10, then it turns blue, and anywhere in between, it's like different shades of green. So it gives you a good rough approximation of the pH. But the benefit, as I said, is that they're easy, easy to use. You just drop it in, and hey, look at the color. pH paper is actually a type of indicator. It's paper that has dried indicator on it. It actually has something called a universal indicator, which is a combination of different substances. Pure pH paper, old-fashioned types, just turns red or blue. Modern types turns different shades, and they give you a more better idea of the specific pH. Again, approximate. Now, a much more accurate use, or way of doing it, is with a pH meter. All right. And we will hopefully be doing and using this in this class. But a pH meter is simply an electronic device that measures pH. Now, it is more complicated to use and obviously more expensive since it's a piece of hardware because it has to be calibrated. But once it's calibrated and if used correctly, they tend to be extremely accurate. Now, the last thing I want to talk to you about is a concept known as a buffered solution. Now, buffered solution, this gets a little bit complicated here. But what a buffered solution is simply a solution that resists a change in pH when either an acid or a base is added. So that if you have this buffered solution, you add some acid, but the pH doesn't change, it stays the same. All right. And the way it works is that if you have a weak acid in solution, like in equilibrium, and then you add a lot of its anion, whatever it turns into, then it will buffer that solution. For example, here we have our acetic acid in water equilibrium solution, or excuse me, equation. And in this case, if you had this reaction, all right, fine. But then you had a whole bunch of the acetate, the CH3COO negative, and a lot of the actual acid itself, then it would be a buffered solution. Okay. And the way this works is that it basically uses Le Chatelier's principle and the common ion effect that I taught you in the previous unit. It basically relieves any stress to the system, thereby maintaining the same concentrations of H3O. In other words, if you add a bunch of H3O, then it will shift to the left and keep the basic, it'll bring the H3O back down to the original levels. If you add a base that removes H3O, Then it's going to shift the equation to the right and eventually get back to the basic equilibrium position that it was before. Um, Now, this is used a lot, well, not used, but it is useful in that, for example, our blood has natural buffering systems in it so that even if we get a whole bunch of carbon dioxide, which hopefully you know when you dissolve it in water or blood, it makes it more acidic. Even if we have a lot of carbon dioxide, it doesn't turn the pH in our blood down so much that it actually causes us harm. So it is very useful in that regard. A lot of antacids also have buffers in them, so that if you take an antacid for, if you have too much stomach acid, you have an indigestion or an acidic stomach acid, then it basically will bring it to the appropriate levels, not make it too basic. All right. Now, the last thing I have is one final definition, the third one, of an acid or base. And this gets even more complicated, but not much. And basically says that, well, according to Bronsted and Lowry, an acid is something that donates a proton, but you can't donate a proton unless you have a couple of unshared electrons, a pair of unshared electrons on a different substance that is there so that you can accept that proton. So basically, what this does is it looks at it not from the point of view of what's giving up or what's receiving a proton, but instead what is able to accept a proton or what is able to not accept a proton, basically. And the definition basically says, oh, and again, I'm sorry, it's used for substances that do not contain hydrogen, but still exhibit characteristic acidic behavior. So it's from a different perspective. Acids are considered electron pair acceptors. So if I'm an acid, then I will accept and use a different elements or compounds electron pair. But if I'm a base, then I am something that actually has a pair of electrons that can receive a proton. And therefore I am donating, as it were, the electron pair. A little weird, but you don't really need to worry about it too much. But you do need to kind of know basically what it is. And there we go. Thank you very much.